Hey folks, welcome back to Introduction to Earth Sciences with Dr. Matthew Wielicki. I'm Dr. Matthew Wielicki. Please follow me on Twitter at Matthew Wielicki or subscribe to my Substack, noclimateemergency.substack.com. And please subscribe to this YouTube channel at mwielicki to get more of these free lectures about Earth science. There'll be about another 16 of these. And then we'll have a lecture series about climate as well. But I thought we would get a good foundation into the earth sciences before we start going into climate. So first lecture from this series was about Earth in context and kind of placing the Earth in the universe and in the solar system. And then we talked a little bit about plate tectonics in the last lecture. And we're going to kind of shift gears and start focusing in more and more on the rocky surface of the Earth. So we're going to talk about the building blocks of rocks, which are minerals today. And then we will go into discussing each of our rock types in our next 3 lectures. We'll cover igneous rocks, sedimentary rocks, and metamorphic rocks. And so before we get into those rocks, though, the rocks are essentially built from minerals. They're an aggregate of minerals. And so it seems a logical order to talk about the building blocks first. And so that you can see in the image in front of you are some of the common minerals that we are used to. And we'll talk about some of these names, but we don't really focus on the names so much as more of the general concepts and the more broad ideas that are governing how minerals form. So why should we even study minerals? Well, minerals are the building blocks of the planet. In fact, they make up all the rocks and the sediments that we use. And so if we understand if we want to understand how the planet operates and how things like plate tectonics or volcanoes work, then really it's the minerals that were either being melted or are forming or within the rocks that kind of dictate how the rocks themselves will behave. Minerals are also very important to us as a society. They are all the raw materials that we use for manufacturing, right? Industrial minerals and raw materials. We have our ore minerals, so these are things that we can extract and isolate things like our metals. Obviously, they're also important in terms of gems. Gems are minerals. They're a way to show our affection for each other. They've had a long history in our, being ornamental and things like that. And they also have a very high value. And so they've been also important in terms of wealth concentration. And so minerals are really essential to us, not only for our understanding of how the planet works, but also to us as a society. In fact, if you were born in 2020 in the United States, you'll use something like 3.2 million pounds of raw materials. So minerals and metals and fuels. And, one person themselves probably won't be using 30,000 pounds of salt, but there will be 30,000 pounds of salt used in the infrastructure that you're using as you go through your lifetime. And so we really require our standard of living in the Western world really does require a lot of raw materials. And so this is an issue. We'll talk about renewables and non-renewables and the lifetime of some of our minerals when we get into talking about mineral resources and energy resources. That will be in the lecture 12, I believe. But just for now, we have to realize that we do require a lot of materials to maintain the standard of living that we enjoy. Before we can even start talking about minerals, we may have to actually zoom in a little bit more and start talking about the smallest building blocks of matter. And I fully admit that we can start to go subatomic particles and things like that, but for our purposes, that's a little bit too narrow of a view. So we're going to just basically shrink things down to an atom. So an atom, for our purposes, will be the smallest division of matter, and that can possess chemical properties that are unique to that matter. And we'll talk about what drives those. And so a single atom is usually going to be a single element. That's the smallest amount of something you can have. And that is purely made up of one atom. So you can have one atom of carbon. The carbon is the element. It has unique properties in the way that it behaves. which we'll define in a minute. And that's going to be how we consider essentially our smallest units of matter. We're going to eventually start putting these units together, these elements together, because as you'll see in a minute, that minerals are a combination usually of multiple elements. Sometimes we combine things and bond them together, and they are two or more atoms, so that we would call that a molecule. And so a molecule would be something like H2 or C2 or O2. And if those two atoms that are bonded together are at least two different things, then we call that a compound. And so examples of compounds would be something like water, H2O. There's hydrogens and oxygens bonded together, and thus there are two different elements. It is also a molecule because it is two or more atoms that are chemically bonded together, but it's also a compound because at least two of those elements are different. Carbon dioxide would be another, CO2, or methane, CH4. And so if we think about what an atom is made up of, what we see is that an atom contains a nucleus, so that's at the center of the atom, and that's essentially where all the mass resides. The nucleus contains the protons, those carry a positive charge, and the neutrons, which carry a neutral charge. And we assign each of those a mass unit of 1. And then surrounding the nucleus, we have an orbiting cloud of electrons. And it's this orbiting cloud of electrons that carries the negative charge. Each electron carries a -1. And we think of these as massless, even though that's not totally correct. For our purposes, we can essentially assume that electrons carry no mass. So all the mass of the atom is in the nucleus, but the electrons will become important in terms of how elements will be bonded together. When we think about an atom, here is a schematic drawing of what that would look like. So this is a carbon atom, and if you looked close, you could count 6 little red protons. And I'll show you in a minute on the periodic table that the atomic number of carbon is 6. So if you change that number of protons, you change the element. You see also that there are 6 neutrons inside that carbon, so that carbon would have a mass of 12. And there are 6 orbiting electrons that are going around the nucleus. They each carry a -1 charge, so this would be a carbon-12 atom that is at a neutral charge. It has a charge of 0 because each of the +1 protons is balanced by the -1 from the electrons. It's not really correct to be thinking about the electrons in perfect orbits. They're probably better to be thinking about it as a cloud of electrons. And the image that you're looking here is definitely not to scale. So I like to think of atoms as essentially mainly empty space. And we know that because we can shoot rays through our bodies. We can go and get an X-ray, for example, and those X-rays pass through our tissues relatively easily, but our bones have a higher density, and so we can image, for example, our bones and look if we have a fractured bone. Well, all matter is essentially empty space. The nucleus itself is very small. You can think of it as something like a baseball or a softball on the 50-yard line, and then the stadium is the electrons that are whizzing around that. And this was discovered long ago when we started to actually be able to shoot high-energy particles through things like thin foils of gold. And very smart nuclear physicists started to realize that the electron cloud that goes around the nucleus itself is much bigger than the nucleus itself. And so there's that atom that we were just looking at again in front of you. That's the carbon atom. So remember that the carbon atom has 6 protons. We call that the atomic number. And that really does distinguish one element from another. If you have a helium, it has to have 2 protons. If you have a carbon, it has to have 6 protons. If you change that number of protons to 7, you no longer have carbon. You have nitrogen. And if you change it to 8, you have oxygen. So really the number of protons governs what the element is and really its behavioral characteristics, because carbon behaves very different than nitrogen, which behaves different than oxygen. And so this atomic number, or the number of protons, is really how we distinguish elements from each other. And that's what gives the elements their chemical properties. So this atomic number is really essential in understanding how something will behave. One interesting thing to note here, which we're going to come back to when we talk about radiometric dating and how we know the ages of things like rocks and meteorites, is that there are certain elements that have the same atomic number but a different atomic mass. And if they have the same atomic number, they're the same element, but they have a different atomic mass, means they must have a different number of protons, because remember, if we change the number of protons, we don't have the same element. So we call these isotopes. And the example there is protonium, deuterium, and tritium. These are 3 isotopes of hydrogen. You can see that they're always denoted with an H. They always have a single proton. And so they will stay as the same element. They will behave like a hydrogen element. But notice that in the first one, there are no neutrons. In the second one, there's 1 neutron. And in the third one, there's 3 neutrons. So although the atomic number stays at 1, the atomic mass changes from 1 to 2 to 3. We call these isotopes. And what we'll see is that there are certain isotopes that are unstable. Many are stable, but there are quite a few that are also unstable. And they disintegrate through radioactive decay, which we have a pretty good handle on the rate of that decay. And so what we can do is we can use the rate of this radioactive decay such that we can essentially have clocks in rocks. For example, carbon-14 is the common isotope of carbon that is used for carbon dating. Carbon-14 is produced in the atmosphere through cosmic ray interaction with nitrogen-14, and it is unstable. It has a half-life of about 5,200 or so years, and thus this is a very common way of dating things like artifacts from ancient Egypt or a woolly mammoth that is melting out of a glacier. We can figure out the age of this, and we'll come back to exactly how that's done when we talk about radiometric dating and geochronology. But we wanted to introduce isotopes here because they're very important when we talk about dating, and we're going to come back to that in a few chapters. You're likely pretty familiar with many of these elements in the periodic table. So this is the periodic table of the elements. You can see that the atomic number in this case is denoted above the element name. So we have carbon highlighted there. Carbon has a 6 above it because carbon has 6 protons. And notice, if, like we talked about just a minute ago, if we increase that number to 7, we have nitrogen. If we increase that number to 8, we have oxygen. To 9, we have fluorine. And eventually 10, we have neon. And so that number above is very important. That's the atomic number. You've heard of many of these elements before. These are essential for life. Things like iron that's in our hemoglobin. It's iron that helps us to actually transmit oxygen throughout our body. You may have seen sometimes your veins may look a little bit blue. That's because when iron oxidizes, it turns into a reddish color. And the blue veins are blood that is going back into your heart to be pumped to your lungs to get reoxygenated. The red is always the blood that has oxygen. When you cut yourself, even if you accidentally cut one of the veins that looks blue, the blood will automatically react with the 20% or so of oxygen that's in the atmosphere, and it will turn red. If you have any rust on your car, you may see that it's red. In fact, rust tends to have this orangish reddish color, and that's because the iron in the steel of the body of your vehicle, especially if some paint's been scratched off, it reacts with water that has oxygen plus with the oxygen in the atmosphere and turns into this reddish hue. So iron, for example, is enormously important in our metabolism and bringing oxygen to our muscles. Calcium helps to build our bones. Oxygen, obviously, is how we respirate with oxygen. And so many of these are very important for life, for example, but also just for things like our electronics. There's that lighter blue group of elements at the second to the bottom line. Those are known as the rare earth elements. So these are things like lanthanum and cerium, protactinium, neodymium. These are very important in terms of how we are building a lot of our electronics and our battery storage. And so these elements are essential not only to life, but also to our our standard of living. So these are those two important numbers: the atomic number, that's the number of protons, and the atomic weight, that's the addition of the protons to the neutrons. If you notice, this is a little snippet of that periodic table. Carbon's atomic mass or atomic weight, those two terms will be used interchangeably, is a little bit above 12. And that's because of these other isotopes of carbon. There's a little bit of carbon-13, and there's a little bit of that carbon-14 that we talked about that's unstable. And thus, if we took all the carbon on the planet, it doesn't weigh exactly 12. It weighs 12.01, just a little bit above, because the proportions of carbon-13 and carbon-14 are very small compared to carbon-12. So it's really dominated by the 12, but because there's a few of these slightly heavier isotopes, we see that the overall carbon mass of all the carbon on the planet is slightly higher than 12. Okay, so now we've got some atoms, and we understand how an atom is built and how we can distinguish between elements. Now let's talk about charge. So we've been talking about our carbon atom, and it had the 6 protons and the 6 electrons around it, and so it had a neutral charge. But occasionally atoms will lose or gain electrons, and when they do that, they develop a charge. And so if you give away a negative electron, then you gain you have a positive charge. If you gain a negative electron, you have a negative charge. And so we have terms for these. Any sort of charged atom we call an ion. And if that atom is donating electrons and thus it's taking on a positive charge, we call it a cation. And if it's accepting electrons and taking on a negative charge, we call it an anion. Remember that the nucleus is usually incredibly stable. The nucleus, unless it's a radioactive element and it's going through decay, is really not going to participate in bonding. The bonding is really going to be dominated by the electron cloud that is orbiting the nucleus. We're going to talk a little bit more about nuclei when we start talking about radioactive decay and geochronology, dating things with this decay, and also when we talk about nuclear energy. We've talked a little bit about this already when we talked about how elements are made. Remember that our star is essentially fusing the nuclei of things like hydrogen and helium to make larger and larger atoms all the way up into iron. And then to make the heavier atoms above iron, usually what has to happen is a star has to go supernova. It has to explode. And that's why we say that you're essentially made of stardust, because if a star hadn't gone through its fusion process and then injected that material into the nebula that eventually made our solar system, we would not be here today, because we would essentially only have hydrogen and helium available that was formed in the Big Bang, maybe a little bit of lithium and a couple other things. But all of these other elements that we see on the periodic table that we just looked at are formed in the furnaces of stars. So here's an example of some ions that are bonding together. This is our classic example of salt. So on the left there you see sodium, and sodium has one extra electron that's in its farthest orbit. So it's the one that's bound the least with the least amount of energy to the nucleus because it's farther away. And chlorine has this outer group of electrons that actually has one little gap in it. And so what happens is that sodium loves to donate an electron, and it becomes a cation. And you can see that once it loses that electron, it becomes Na+. And chlorine loves to accept an electron. And so when it accepts that electron, it becomes Cl-. And thus, those things can bond. And what we just were introducing was ionic bonding, which is going to be the first type of bonding that we talk about. So we're introducing elements because eventually the elements are going to bond together to make the minerals, and the minerals are going to aggregate together to make the rocks. And so we're going to discuss a little bit about chemical bonding. Chemical bonds are essentially what holds two elements together. You can almost think of it as the glue that is holding these things together. And there are three different types of chemical bonds. There's ionic bonding, which we just introduced, but we'll take another look at very quickly. Covalent bonding, which tends to be the dominant way that most of the rocks and minerals are bonded that make up the rocks of the planet. And then metallic bonding, which is a unique type of bonding that we'll touch on very quickly, but we won't really focus on. So here's that example again of our ionic bonding. Here is our sodium cation. It has donated an electron and taken on a positive charge. Chlorine has accepted that electron and taken on a negative charge. It's our anion, and thus opposites attract, and so we make a salt mineral that we call halite from sodium and chlorine bonding, NaCl. Now this mineral isn't very strong. This is a fairly weak bond, and how do we know that? Well, you can take a little bit of salt and put it in some water. It doesn't really always even need to be warm water. Stir it up a little bit and you'll actually break the sodium and chlorine bond, and you'll have sodium and chlorine ions floating around in your water. And so this is a fairly weak bond. This is the mineral halite. This is what it looks like in real life, and so you can see this ordered structure to it. We're going to come back to this in a little bit, but if you've ever seen salt and you spilt salt on the table, you notice that they're in these perfect little squares, and there's nobody out there with tiny little hands that's cutting perfect little squares of salt crystals. It's actually because the sodium and chlorine ions are arranged in this cubic fashion, and even when the halite mineral grows, which is our natural crystal of salt, of NaCl that you can see in the right image, you can see these little squares. And so something about the order, the atomic order of the mineral, of the elements inside that make the mineral, can dictate what the mineral is going to look like in its outer form. The second type of bonding is not donating or accepting electrons and then gaining charge. It's actually sharing electrons. And so here is an example of two atoms, and notice that they are sharing their electrons. There's a couple electrons, a pair of electrons that are now what used to be doing an orbit around the nucleus. You can think of them doing a figure 8 around both nuclei. And it's this covalent bonding that is very strong. This is how the majority of things that are bonded together, for example, H2O. Water is an incredibly strong molecule. You can boil it and put a bunch of heat to it, and the water molecule doesn't break apart. It stays as H2O, but it will go in the vapor phase. It takes quite a bit of energy to break apart the bonds between hydrogen and oxygen because, for example, water is covalently bonded. Here's an example of that covalent bonding. They are sharing these electrons. These electrons are doing these figure 8s around the oxygen nucleus and the hydrogen nucleus, and thus it's a very strong bond, much stronger than, for example, the ionic bond that we were just talking about with salt. Metallic bonds are very unique. Metallic bonds are essentially bonds that allow electrons to move freely from nucleus to nucleus. And this is really important if you want to have, for example, good conductivity, and you want something that is ductile but still pretty strong. That's what metals are. Metals are malleable, they can be shaped, they can be pulled into thin wires, and they're really good conductors. Thus we can introduce a charge on one end and we can receive that charge coming out the other end. So metallic bonds are unique in the fact that they allow electrons to effectively move like a sea between all of these, all of the nuclei, and they're very important in terms of our electricity and a lot of our building infrastructure. But we're not going to focus on them so much because really it's the core that's metallic, and most of the mantle and the crust is made of elements that are covalently bonded together. We're going to come back to this a little bit when we talk about raw materials and mineral resources. So just to cover some of those basics, remember that a molecule is two or more atoms bonded together. A compound is two or more different atoms bonded together. What does that mean? That means that all compounds are molecules, but not all molecules are compounds, right? That O2 molecule up there is still a molecule, but it's not a compound. H2O is both a molecule and a compound. So that tends to throw people off a little bit, but that's just some terminology that you'll have to get used to. Minerals have a chemical formula, so we like to express things in the written form such that we can define what elements are there and in what concentration. So for example, when we talk about water, we write out H2O. Now notice H2O doesn't really tell you much about the structure of the water molecule. In fact, it'd probably be better if we wrote it HOH. But for brevity's sake and for simplicity, we write out our chemical formulas with the number of the atoms that are bonded together, but you don't get much information in terms of what's bonded to what or what the structure of the actual compound looks like. So why does the bonding matter? Bonding matters because how things are bonded can dramatically change how they behave. In fact, some of you may have a pencil in front of you and you may be wearing some jewelry with a diamond in it. Both of those things are pure carbon, but notice they behave very differently. You can take your pencil and weakly pull it along a piece of paper, and what happens in graphite, which is what is in your pencil lead, it has these sheets of graphite that are very weakly bonded together, and so you don't need a lot of force, and as you slowly move it across a piece of paper, you leave a line behind as these sheets of graphite are breaking off and they're being deposited on the paper. It's relatively soft material. You don't have to press very hard to write with a pencil. Diamond is the hardest known substance, natural known substance on the planet. And it is also exactly identical to the graphite. It is just purely carbon. Except that carbon isn't bonded into these weak sheets. It is bonded very strong between all of the carbons next to it. And so the bonding of things really does dictate how things behave. And so it's very important for us to understand how things are bonded if we want to understand how certain minerals and elements behave and how drastically different they can behave, even though they're both, in this example, made of the same thing, pure carbon. So let's define a mineral. For our purposes, a mineral must be a naturally occurring solid formed by geologic process that has a crystalline structure and a definable chemical composition. We're going to focus on inorganic minerals, but I'll show you some examples of things that are not inorganic, some organic minerals, and realize that this definition is relatively imprecise. If you look this up, you'll probably find many definitions, but for our purposes, we're going to stick with a naturally occurring solid formed by geologic processes, must have a crystalline structure, and must have a definable chemical composition. So what's that mean? Well, that means that, for example, industrial diamonds are not going to be considered a mineral. They're a synthetic mineral. They're very important in terms of our ability to do many things and drill and cut through very hard materials. But because they're made in an anvil, they're made in these really large presses because diamond requires a huge amount of pressure. We don't consider that natural. It fits all of our other definitions, but because it's synthetic, we would not consider that a mineral. A mineral has to be a solid. It has to be in the solid phase. It cannot be in the liquid or gas phase. So things like oil or natural gas would not be considered minerals. But something like ice would be considered mineral. Ice is a naturally occurring solid. It's formed by geologic processes in cold environments. It has a fixed chemical structure and a definable chemical composition, which, is H2O. Minerals we must be able to define and describe a mineral with a chemical formula. It can't be an infinite amount of different things because then it doesn't really tell us anything. And so we have to be able to write out the chemical formula of the mineral. This is, again, halite, the mineral halite, which we know as salt. You can see that cubic structure again, and the sodium cations and the chlorine anions that are bonded together through ionic bonding. And we can write out the chemical formula for halite as NaCl. Some minerals can be relatively complex in their chemical formulas. This is the mineral known as biotite, and you can see that it has quite a few of different things that go into it. And sometimes things can be a little bit, there's some freedom of movement. So you'll see that it's a potassium, and then you'll see magnesium and iron with, in parentheses with a 3 below it. That means there's 3 magnesium and irons, and they could be 1 magnesium and 2 irons, or 2 magnesiums and 1 iron. So there's some freedom in substitution here, but pretty much anything that has this general chemical formula, we would call the mineral biotite. And so we have to allow ourselves a little bit of variability because nature's messy and things will substitute in for each other, especially things like magnesium and iron that have relatively similar sizes and similar chemical properties. You can substitute one for another. So this is just to highlight that some minerals can be very complex, while other minerals can be relatively simple. A mineral must have a crystalline structure. So these are 2 minerals of the same thing, SiO2. These are 2 compounds that are the same thing, SiO2. The top one is quartz. It's a mineral. It has a crystalline structure. You can see that all of these little circles are ordered in some manner. Glass, which you see at the bottom, that's obsidian. You may have seen obsidian before in terms of arrowheads. It was a common tool used by Native Americans because it can get incredibly sharp. The reason it can get incredibly sharp is because it is what we call a glass. And glasses, by definition, even the glass that you may be looking out your window at right now, they are essentially a non-orderly crystalline solid. And the reason they're not orderly, they're actually done on purpose. So to make glass, we heat up silicon and boron and a few other things, and then we quench it. We cool it very rapidly because we don't want the glass to order itself. When the glass would order itself, what that would do is that would distort how the light is passing through the glass, and we don't want the light to be distorted because, for example, if you're driving in your car and you're looking at your windshield, you want to make sure that what you're seeing through the windshield is actually what's happening. You don't want things to be appearing in any sort of different manner. And so in terms of what we consider a mineral, we would consider the quartz a mineral in the upper picture, but the obsidian, even though it's also made out of SiO2, essentially the same compound, would be not considered a mineral because it's a glass, and thus it doesn't have this ordered crystalline structure. It's a disordered solid. These crystalline structures, we come back to this, these crystalline structures can actually be evident in the mineral itself. So remember, we talked about sodium and chlorine bonding into this cubic formation, and you can see that crystalline structure in the shape of the mineral halite as it grows. And so usually something about the mineral form tells you about what the bonding order and structure of the crystal lattice looks like. Here's some more examples. So there are these quartz crystals that you can see. Quartz has this pyramidal termination. Diamond usually has these 2 pyramidal terminations on both sides. Halite in the upper left is our salt example. And so something about how these crystals form tells you something about the internal structure of the crystal lattice itself. We'll see that in nature, a lot of times the minerals don't have room to grow into their preferred shape, and so usually the minerals are all competing for space. And so usually if you find a diamond, for example, it won't look like a beautifully cut diamond. It'll actually won't even look like these 2 pyramidal terminations. It'll be pretty rough because as that diamond was forming, it was competing for space, and it just kind of fills in where it can. And thus we usually take raw diamonds and we'll cut them into those beautiful gemstones that we're all so familiar with. So remember, I mentioned that most of what the minerals that we'll focus on are organics, but not all minerals are organics. So here's some of the examples of inorganic minerals. For example, a clamshell. the calcium carbonate that or the aragonite that the shell is making, its exoskeleton to protect it, your bones, your teeth. These are all organic minerals, but of the close to 5,000 minerals, there's just a handful that are related to organic processes. And so because this isn't really a biology class, this is an earth science class, we're really just going to focus on the inorganic minerals as opposed to the organic minerals. When we talked about the bonding of two different minerals, we used this example of diamond and graphite in your pencil. We call those polymorphs. So polymorphs are minerals with the same chemical composition but a different crystalline structure. Right? And we already talked about this a little bit. The diamond in your ring and the graphite in your pencil are essentially polymorphs of each other. They are both pure carbon, but how they are bonded dictates how they behave. So just to recap, a mineral requires essentially 5 things. It has to be naturally occurring. That essentially means it's formed geologically. It has to be a solid. It has to have a crystalline structure, and it has to have a defined chemical composition in order for it to be considered a mineral. Mineral crystals grow in a few different ways. We're really just going to focus on the first 2 a little bit, but so they can grow through the solidification of a melt. So in the next chapter, we're going to talk about igneous rocks. These are rocks that form from molten rock, from a liquid, and they essentially freeze into a solid. They can also be precipitated from solution. So if you've ever seen salt ponds where they trap salty water, they allow it to evaporate. That will leave behind the halite, the raw mineral of salt, that we can then collect and process a little bit. Well, we won't focus on these next 3 so much, but they can also be formed by solid state diffusion. We're going to talk a little bit about that when we talk about metamorphic rocks. We'll see that there is this rock type that gets heated and exposed to high enough pressure where things start to change. You can actually drive reactions, but it's happening in the solid state. They can happen through biomineralization, like the clamshell that we were just looking at, and they can sometimes be precipitated directly from a gas. We'll touch on this a little bit when we talk about volcanoes in chapter 5, or in lecture 5. So most crystalline minerals will never be able to grow into their preferred crystal shape. You may have seen geodes before, so that's an image of a geode down below. That purple hue is amethyst. That's quartz with a little bit of an imperfection that gives it this beautiful purple color. But we have to realize, as we mentioned before, that most of the time minerals are competing for space. And so although a quartz crystal would like to grow into this nice pyramidal termination, when it grows in nature, it's usually competing with other minerals around it. And so most minerals will be anhedral. Anhedral means that they're just filling in any space that they can. They're not really taking on their crystal shape. But occasionally, like a geode, for example, which is a rock with a cavity in it, and that cavity allows the quartz crystals to grow without any impedance, slowing them down or changing their shape, we call those euhedral. So occasionally we have beautiful euhedral crystals. They tend to be stuff that we like to display and use as ornamental pieces. But most of the time, in most of the rocks that you're familiar with and that we're going to look at throughout this lecture series, most of the minerals are anhedral. There's a lot of physical properties that we use to identify minerals, and so we're just going to touch on each of these very briefly, but this is essentially how we would identify minerals out in the field. One way is through color, and unfortunately color is not a very good diagnostic of minerals. And so these are all quartz. That's milky quartz on the left, that's our regular clear quartz in the middle, and rose quartz on the right. Remember, we just showed a picture of amethyst, which is also quartz. It was purple. We have things like smoky quartz, that's black. And so what we find is that just a little bit of imperfections in a mineral can really drive a color change in that mineral. So color is not the best diagnostic feature. In fact, what's better is the color of the powdered form of the mineral. So you may sometimes see geologists out in the field and they'll have little ceramic plates with them, and what they'll be doing is they'll be scratching the rock on the ceramic. Ceramic is a very strong and hard substance, And so that ceramic will usually mean that the rock will disintegrate and powder. And that powdered form of that rock is much more diagnostic than the color of the rock itself. So in this example, this is hematite, kind of has this gray to black hue to it. But notice that when you streak it, when you scratch it onto the ceramic plate, you see this distinctive brown color, and that color tells you that you're actually looking at hematite. So instead of using the color of the mineral itself, we use the color of the powdered form that we streak onto a porcelain or ceramic plate. The luster is important about distinguishing between non-metallic and metallic minerals. So again, the luster is something like the shine, the amount of reflected light. Most people think of chrome, a chrome bumper, right? That has that metallic luster that we're used to assigning things with metals. The two minerals on the right of your image, those are feldspars. You don't see that same luster. And feldspar is a non-metallic mineral. Pyrite on the left, that's fool's gold. That is lead sulfide, and that is a metallic mineral, and you can see that luster. Pyrite uniquely also has a cubic structure, very similar to halite, and you can see the cubes of pyrite there that are growing. Another way is through the hardness. This is one of the best diagnostic features, and this was determined by a famous German scientist by the name of Mohs. And so you can see at the bottom there's Mohs number, so that's an arbitrary scale. That's why there's no units. You always have to be very wary of scales without any units, because somebody just basically said, I'm going to order these things from the softest naturally occurring substance, which is talc, to the hardest naturally occurring substance, which is diamond, and I'm going to put it on a scale of 1 to 10. And so that's completely arbitrary. The units of actual hardness you can see there on the y-axis. And so there is this exponential hardening as you go towards diamond. And diamond really is the strongest naturally occurring substance on the planet. So what we do a lot of times is we scratch one mineral onto the other if we don't have a clear distinction between the two. And we can look at graphs like this to help us determine which is which. The specific gravity is another way that we can distinguish minerals. So this is essentially the weight of the water divided by an equal volume of water. So the weight of something like lead sulfide or galena. Oh, sorry, I said pyrite was lead sulfide. Pyrite's iron sulfide. Galena is lead sulfide. This is an ore of lead, PBS. And lead is a very dense and heavy material, so it has a very high specific gravity. If you picked up a little bit of galena and it was the same size and volume as, for example, talc, which is baby powder, you would see you'd feel a very large difference in the heft. The galena would be very heavy for the same size of material because of the elements that are inside it. We also use this crystal habit that we talked about before, right? That's the external expression of the mineral's internal structure. So we've already talked about this extensively, things like halite or quartz. We know something about the external crystal habit tells us something about what's happening on the inside. And also the cleavage. So this is how the certain minerals will cleave or break. And that example in front of you is a mineral called calcite. And if you look close, what you can see is that all the little chunks tend to have this rhombohedral look to it. And that's because calcite has 3 planes of cleavage that essentially make a rhomb. And so if you hit it with a hammer, nature is going to take the easy path, and it's going to break along these planes of weakness. And thus, as you break apart calcite, it tends to continue to break in these little rhombs. Very analogous to, for example, salt. If you take salt, it also has these 3 planes of weakness, but they're in a perfect cube. You keep breaking apart the mineral halite, and you keep getting smaller and smaller cubes. And thus, when you look at your salt shaker, for example, and you spill a little salt on the table, they look like perfect little squares, right? And so these are what we call cleavage planes. If a mineral doesn't have these planes of weakness, then it will break in a very disordered fashion, which we call fracture. So this is an example of something like garnet or of some quartz, but it's obsidian. So it's this glassy form of quartz. And notice that you don't get these nice flat structures. You get very irregular breaking. If you've ever broken a piece of glass, you've probably experienced this, where it doesn't break along nice ordered lines, because by definition, a glass is a disordered solid. And so there are no planes of weakness. And so when there are no planes of weakness, we call this fracture. And then there's a few others, for example, magnetism. Certain things like magnetite are magnetic. We can check if things react with acids. We can look at double refraction. So notice that the calcite, that's the lower picture, that is a calcite mineral that's sitting on top of the word calcite, but it's doubling the light that's coming off of that. It's actually splitting the light into two that's reaching your eye. And so you can imagine making a windshield out of calcite would be a very bad idea, because the car in front of you would look like two cars and you don't really know which one is which. Taste, so halite obviously tastes salty because it's NaCl, it's literally salt. Sometimes smell, so things like sulfur will have a distinct smell. So we try to combine all of these in the field such that we can make accurate determinations of what minerals we're looking at when we're out in the field. When we talk about mineral groups, there's quite a few important mineral groups, but we're really going to only focus on the silicates because they make up 95% of the continental crust. And so that's what we'll focus on, but we're going to touch on some of these others as we go through the lecture series. So what's a silicate? A silicate is a mineral group that is essentially made of a silicon atom that is surrounded by 4 oxygen atoms. We call it the silicon oxygen tetrahedron, SiO4, and it's the fundamental building block of essentially the entire mantle and about 95% of the continental crust. So it's a very abundant in the percentages of the planet, and the Earth's crust is very abundant in silicon and oxygen. So it should make sense that this becomes the fundamental building block of essentially most of the mineral groups that make up the mantle and the crust. And it's really how these silica tetrahedron are ordered and bonded together that gives us all of these different types of minerals that we'll eventually start talking about that are going to build our rocks. And they can be isolated tetrahedrons, they can be single chains, double chains, two-dimensional sheets, or three-dimensional frameworks. And as you progress between these, you go into a different mineral class. And again, we're not going to focus so much on the names like pyroxene and amphibole and quartz and feldspar. I'd rather the big picture of the silica tetrahedron is the building block, and how you put those together, and you can just imagine single chains, double chains, sheets, three-dimensional frameworks. That's going to dictate what type of mineral you have. And when we talk about minerals, we ultimately classify them into a class of ultramafic, mafic, intermediate, and felsic. I like to just focus on the felsic and the mafic because if you know those two, well, then intermediate is just in between felsic and mafic, and ultramafic is just more mafic than mafic. So what does mafic mean? Mafic comes from the term magnesium and the Latin for iron, ferric. These are rocks that don't have a lot of silica in them. They are relatively simple structures. They are dark in color. Because they have a lot of iron and magnesium, that's the name mafic comes from, they are high in density. So they're very different than what we call felsic rocks. Felsic comes from feldspar and silica. These are rocks that have a lot of silica. They tend to have a very complex structure. They don't have a lot of iron and magnesium, which means that they're relatively light in color and they're low in density. When we started talking about plate tectonics in the last lecture, we talked a little bit about what the oceanic crust and the continental crust looks like. The reason that the oceans exist where they do is because the oceanic crust is mafic, and mafic rocks and minerals tend to be high in density. The continental crust is felsic, and felsic rocks and minerals tend to be low in density. And so the oceanic crust sits a little bit lower than the continental crust, and when you pour water onto a dry planetary surface, the water fills in the low-lying areas, and thus the oceans exist where they do because of the rock type that is making the crust below the sea. right? And so it's the oceanic crust that's predominantly made out of mafic minerals that drives where the oceans are. We're going to come back to these words mafic and felsic a lot when we start talking about, in the next chapter, our first rock type, which will be igneous rocks, and even when we talk about things like volcanoes, because you'll see that it's the composition of the magma, whether it's mafic or felsic, that really dictates whether or not you have a gentle or what we call effusive eruption, something, for example, like Hawaii, where you're not so worried that the mountain's going to explode, or something analogous to Mount St. Helens, where literally half of the mountain explodes off in a single event. And it's really the composition of the magma below the surface that's dictating how the volcano is going to behave. Well, so that covers minerals. We're going to keep touching on minerals as we go into our rock types for the rock cycle. If you're enjoying this lecture series, please subscribe to the YouTube channel so that you get notifications when I put out a new lecture. Please follow me on Twitter at Matthew Wielicki on Twitter, and follow my Substack, noclimateemergency.substack.com. As always, thank you for the support. If you have any questions, please post them in the comments and I'll do my best to address them.